For our final design, we created a biosand filtration system. The inspiration behind our design is to help people living in parts of the world where clean, drinkable water is not available. In many communities, people lack facilities that provide treated water, and in other places, water sources are polluted or unsafe. Our topic centers on providing a simple and reliable way for people to get clean water with ease, using a system that does not require electricity, chemicals, or complicated equipment. The problem we are trying to solve is that millions of people in the world still do not have access to clean drinkable water. Contaminated water can carry dirt, bacteria, or harmful particles that lead to serious health issues. Our goal was to design a filter that could take in dirty water, meaning cloudy, full of debris, or otherwise visibly contaminated, and produce water that was safe to drink. We wanted it to be low in cost, easy to use, and easy to understand. It should be effective in areas where resources are limited.
The core of the design problem is that safe water is not always available, and solutions that exist are either too expensive or too complicated. We were targeting to make something simple. Pour water in at the top, let the filter layers do their work, and collect clean water at the bottom. Potential customers could be any person in need of clean water, living in a remote community, a developing country, a natural disaster-affected area, or even a temporary situation when clean water isn't available. Our project encompasses both general and specific performance expectations. In a general sense, the system should be able to intake dirty water and filter out as much of the visible debris and contamination as possible. More specifically, when the dirty water is poured into the top of the filter, larger objects are caught at the top within a sheet metal barrier. Next, the water continues down into the sand layer where smaller particles become trapped. Under the sand lies the gravel zone, supporting the sand and preventing the outlet tube from clogging. After reaching the gravel, the water moves through the tube and exits the filter as clean water.
One of the unique features of our design is that the inside of the filter is visible. Customers can actually see filtration as it happens. On one side, we used plexiglass so that they can see the water move through each layer. Instead of just telling them what was happening inside a sealed container, they could watch. This makes the design far more interactive, educational, and engaging. It further adds value in that the system is portable, lightweight, and easy to transport to places where clean water is needed. Another unique feature of our design is our pH sensor, which lets the user test the water after going through the filtration system. If the light turns green, that means the water is safe to drink, but if it turns red or yellow, it's not. In creating our design, we analyzed various communities around the world lacking access to clean water and researched common methods of purifying it. We studied traditional biosand filters to understand the right combination and placement of layers, along with which materials work best. We then adapted those into a smaller, more portable prototype. We worked with different materials and methods of construction during the building process. We tested attachment methods for the plexiglass, how much sand and gravel to use, and how to keep the system sealed. These steps led us to our final prototype.
The most exciting part of our project was testing and verification. We poured dirty water into the filter containing sand, leaves, and dirt. As the water traveled through the layers, we watched it become clear. When it exited through the outlet tube, the difference was very noticeable. The water turned from a murky brown color to clean, clear, and safe to drink. This testing demonstrated that our prototype works as intended and can be repeated over time. Our design changed several different times throughout this process. Initially, we were going to attach the plexiglass with sealant alone. We later learned that the sealant wasn't strong enough to hold the weight of the sand, gravel, and water. To fix this problem, we decided to use thicker plexiglass and add screws for additional support, even though it was less cost-effective. The sealant was used to prevent leaking, which made the overall design much stronger. We also learned that even after improvements, an even thicker sheet of plexiglass would prevent cracks. Our final design costed us $147.42, and the materials included were plexiglass, silica sand, 2 sizes of drainage gravel, sheet metal, waterproof sealant, PVC pipes, an outlet valve, and a 5-gallon bucket, creating a reliable filtration system at a low cost. In conclusion, our prototype demonstrated that dirty water can be turned into clean, drinkable water using simple materials. This design has the potential to help people anywhere in the world who need safe drinking water. Some lessons learned from this project included filtration challenges, design challenges, troubleshooting, time management, and how engineering can truly address worldwide problems. Thank you for watching.